Day of lectures of this winter school. Can you hear me? Yes. Okay. I didn't say much yet. Good morning, everybody. Today's first speaker is Reynier Peletier, who's his third lecture. Welcome.
Okay. So, today can you hear me? Is the microphone working? Oh, good. Today I will, as I said, I will talk about stellar populations in galaxies, and especially nearby galaxies. The methods have been dealt with the previous two lectures, and so this is the real stuff. This is what you see. So I'm trying to give an emphasis on certain things that we see around us and how we can interpret these things, and then with a little bit of ideas behind this about formation and evolution of galaxies. So this plot is extremely, it's good to start with it, I think, because it's fundamental that the morphology density relation, that in high density environments that the fraction of E's, ellipticals and zeros is so much higher than in low density environment, and opposite in low density environments the spirals dominate. So this is of course confirmed by the Sloan Digital Sky Survey. You see that the higher the density becomes, the more important the red sequence becomes at the expense of the blue cloud. Note that in Sloan we are really talking about bright galaxies still. If you go to the luminosity function, these are also some, the paper on the right is also a very classical paper, where they give the luminosity function of the Virgo cluster and the luminosity function of the local field, and it's the same thing as being seen. So in the Virgo cluster, dominating objects are especially the dwarf ellipticals, and plus some bright galaxies, all kind of bright galaxies. Virgo doesn't have a very high density environment, so it could be the fraction of ellipticals versus spirals could be higher in the cluster. And in the field, the dwarf elliptical fraction is very low. Basically, the only objects that are found are the ones are companions to brighter objects. So if you compare this with Sloan, you see these are the blue objects in Sloan, these are the red objects in Sloan. You see something similar to the field, except that you have to realize that this is something like 2.5 decades, correspond to about 6 magnitude and a bit, is from here to about here. So you start seeing this increase of irregulars going up. Good. So once this is the world in which we live, so everything has to fit in this. And what I'm going to talk about is now about the details. So the details of the galaxies. I don't want to consider just galaxies being part of the red sequence or in the blue cloud or whatever. I like to see what's happening inside galaxies and whether we can understand things by looking in detail in galaxies. First, a little bit on scaling relations, some way of learning, although it's still not very detailed. Then going inside the galaxies, doing measurements with correct, with some kind of normalized aperture, central regions, and then regions farther out. I'm not going to go to really outer regions. That's just, there's no time. I started noticing that I have to skip quite a few things that I wanted to say, even not in my lecture tomorrow. But that's, of course, unavoidable, and for that reason, it's because the field is still really a very big field. And then about M/L ratios, which are also an important thing. So, scaling relations, just a few sentences about this. It's probably obvious, but scaling relations, for example, the relation between color and luminosity. Luminosity is some indication of the size of the galaxy, the mass of the galaxy. And color is an indication of populations. So it is, in fact, it's for a galaxy the only real way, if you cannot resolve it, to combine, to link populations and structure, morphology, dynamics. So this is fundamental. And okay, if you can resolve objects, then of course it's not that fundamental anymore, but the scaling relations for unresolved objects are fundamental, and that's the way that people learn something about evolution and so on. Of course you have to understand the relations also, but the fact that there is a relation is already something, and you can use it then to, for example, look at it as a function of redshift. Then you don't really even have to understand very much what the relation means. That comes second. That's the secondary thing. So it's a very important tool. So this one, so basically the red sequence, the color luminosity relation, this is the one in the coma cluster. So the coma cluster is a rather high density environment, and what you see in coma is, this is a very famous work of the Durham group, Richard Bauer, John Lucy, Richard Ellis, and students. What you see here at the bright part, only ellipticals and the zeros. So the fraction of spirals in the coma, in the inner region of the coma cluster, is non-existent. But what you do see is that these early type galaxies, elliptical and spirals, at least for a certain range, fit on a very tight relation. And the deviations from it, well, say spirals are very much away from the relation. And if you go to the lower end, so fainter galaxies, you start seeing a lot of deviations. But note that above the line, there's very few galaxies. And probably if you look in detail, most of the deviations are caused by this thing we discussed, and also Daniel Gazzetti, dust extinction. So this part is starting to get messier. This part is still very clear, and this is then the way that people define the red sequence, and they see it in all clusters. The fact that you have the spirals down here, the bluing, is often interpreted as just a vector going this way. So population, which in principle, if you have an old population sitting here, and you get a burst of star formation on top of it, what you get is a slight increase in luminosity, okay, a little bit this way, but mainly a bluing of the object, so you go this way. And you can interpret that. You can even interpret this object like that. So in principle, it should have sat there. You get a little bit of a burst of star formation, some fraction of young populations. It goes down and up a little bit because it's a bit brighter. So that's the main idea, and the interpretation that way can lead to quite a bit of things along the sequence. So why is there a slope in the sequence here? The idea generally is that there's a slope, that galaxies, the redder they become, the brighter they become, the redder they become, that slope is caused by metallicity. So the metallicity of the galaxy becomes larger, so they become redder. And this is seen, in fact, in all colors, as we'll see, or in many colors, as we'll see. So nowadays, this is the newest. This is a color magnitude diagram from the COMA ACS survey. So the difference with this is, if you compare in detail, is that there's a few more magnitudes. We went deeper, a few more magnitudes, as more galaxies. But you start here coming into the problem that you don't know membership. So many of these objects are behind the cluster. And so you need redshift and things like that to really make sure which ones are member. The big symbols are member of the coma cluster. Then there's some objects lying out here. These are also ellipticals, but these are so-called compacts. And no, they're not the compacts, sorry, that's wrong. These are the spirals, sorry. There's a couple of them out lying above the line. And these are so-called compact ellipticals. And they are redder for their luminosity. This will come back. So rather than luminosity, you can just as well put velocity dispersion for early type systems on the axis. Since there's a very good relation between luminosity and velocity dispersion, so the amount of random motions in an object is a good measure of, is a good indicator of the mass in the object itself, and somehow and does correlate very well with luminosity. Whether we completely understand it is not that clear. I'm going to go. That's probably going to be tomorrow. I'll go into that relation a bit more in detail. Here, this is also by Bauer et al. And you see that there is also a very tight U minus V versus sigma relation. And there's more. I mean, these relations already date back to people like Vogel, 1978. And they're not that different. Of course, in Bauer et al., the scatter is very low. The main reason is that they use very small inner apertures. And I don't know, it's very difficult to reproduce that kind of small scatter, but they have been very careful here. But you see that this relation, it can be used for U minus V, V minus K, J minus K, and then there's a color relation as well. In fact, it looks to me, from these diagrams, that stellar populations in ellipticals and zeros seem to be a one-parameter family only. Well, then I would be very quickly finished my talk, then it's done. But so it's not the case. But it is actually, to first approximation, if you are in the centers of clusters. So in the centers of clusters, the situation is relatively simple. You have mostly ellipticals and S-zeros. And also, the scatter, so the ellipticals and S-zeros there have a much lower scatter in a scaling relation like that. So it is probably reasonable to estimate they all have similar ages in a cluster like that, so that you have indeed more or less a one-parameter family. But of course, we are not all sitting in the centers of large clusters, of able type 3 clusters. So, well, the answer is probably no, but let's start to develop this argument a bit. So, stellar population in 0D, just apertures. But apertures with knowing a bit more about the surroundings, so how you select things and so on. This diagram is also a classical diagram. I've often wondered, when I did my thesis, this Jesus Gonzalez at LIC was doing his work at the same time. And for using the relation, the diagram between a metal index and H beta, he determined ages, SSP ages, and metallicities for elliptical galaxies. This was a sample of elliptical galaxies. This was the standard sample. At that time, there was very little else than for line strength than the work of Gonzalez. So what he gets, if you interpret this diagram, so these are lines of constant age, these are lines of constant metallicity, you get that basically all the ellipticals and S-zeros on this diagram have metallicity around solar, and that the ages, that it's a sequence in age. That is really strange, especially with, in hindsight, the fact that you have this color sigma and color luminosity diagram. So what's happening? The answer comes here. This is the thesis of Harald Kunschner, and also in Durham. So he takes the Fornax cluster, so he takes this environment, this is all kind of ellipticals everywhere. So in fact, it's mainly field, it turns out to be. But here's the Fornax cluster, and you see, in fact, that they follow a metallicity line, a constant age line. Plus the fact that there are some objects above this. And if you look in detail at those objects, those are mainly smaller. So apparently the brighter galaxies have the high metallicity, and they fall out here. And some other objects have younger ages, indeed. So here you do have this fact that you have this line strength sigma relation somewhat, plus objects that scatter below it. So that does make sense again. But it's not really completely okay yet. So now, without going into very much detail about the instrument, let's go to the sound sample and see what comes out from there. Sound sample is 48 ellipticals and zeros in the nearby universe, some in the Vogel cluster, some in the field, and what we measure here is H beta emission, H beta cleaned from emission, MGB, there's another iron line here, and it's integral field spectroscopy, so you get line strength maps, kinematics maps, and all kind of things. And I don't want to go that much in detail about the sample. So about the details of the instrument. So the sample is these two panels on the left, the middle and the left panel. This is the sample is uniformly selected in ellipticity and luminosity, and that's as good as it gets. It's difficult for S0s, for example, because the ellipticity, where do you measure the ellipticity? Note that in all the Sauron papers, there's never a real distinction being made between ellipticals and S0s. In none of them. So there is, we just talk about them like early type galaxies. There's sometimes later the SA sample of Sauron comes in. Those are 24 spiral SA galaxies. SA selected from the RSA, Sanish-Taman. So, okay, these objects, so the spectra have all been cleaned from emission, as I explained in a previous talk. What you find is that 70%, 75% of ellipticals and the zeros contain emission in the center, near the center. And in fact, it's mostly extended also. That fraction is higher than was known before, but it's a considerable fraction. I'm not going to talk about the gas kinematics here. It generally is decoupled from the stellar kinematics, but there's a lot of things to be said about it, but that's not part of this. Of these series of talks. So the field, the galaxies are covered, the region that's covered of the galaxies goes more or less up to 1 RE, sometimes in the mosaic, sometimes in one pointing, and sometimes a slight aperture correction here is applied. So, but it's small. So what we're talking about here is global values, sometimes it's in RE over 8, sometimes it's in RE. So, this is the diagram from the Sauron data. So, you see here, there is here in this plot, there's a distinction made between E and the zeros, okay. So you can see that the ones that were classified E fall in like that, fall here mostly old, zeros also, and then some of them fall above the relation. So it's very similar to Kunstler et al. And consistent with others in the literature. This is Sloan, this is Kunstler paper, this is Thomas et al. So, now let's see whether population has anything to do with kinematics. So these are all the velocity fields of the 48. So they arranged, they are done in a grid, going from slow rotators, so these objects here on here, they have no, or they start having almost no rotation at all the way going to fast rotators. So this parameter lambda r, which determines, in fact, a two-dimensional v over sigma, is going that way from left to right. These are rotationally supported. In fact, most of them, many of them are. The majority of the galaxies rotation is supported. Okay, so you have these galaxies. If you then plot, you color the points according to fast rotate, slow rotator, you see something very similar as for E and S0. But there's very few slow rotators, only 7 or so. So the slow rotators, all of them are here, are old, and the fast rotators are old and younger. Good. This is inside RE still. These are some average values. So, now like a index, like a color sigma relation, here you can plot index sigma relations. And you can do the same thing. If you have some relation defined, some average relations on which you mainly the bright galaxies are, because there's very little scatter out there, and you just draw this line, you continue this line, then the deviation from that should say something. You could consider that like a sequence of metallicity, on which young population cause a deviation. And in that case, you should not take these dotted line, but you should take a line like, you should take an upper limit, because then you can go down. And so in this case, you take a lower limit, and younger population cause its rate to go up. And the same with iron. So what do you see? Very similar to color sigma relation. Most bright large galaxies are on the relation, and if you go towards the fainter galaxies, but that's not that faint, it's say a velocity dispersion of 100, you start moving off. So you have an addition, a considerable addition of young populations. That's from the scaling relation. Later we'll see if that's really the case. S0s and ellipticals out here on these diagrams seem to be fairly mixed. So that for sure. The long rotators are all lying there. They're all old. But the ellipticals and zeros are mixed. And cluster and field in this case also doesn't seem to make much difference. Well, it's not really cluster. I mean, cluster is Weber cluster. The density of the Weber cluster is such that even in very close to the center of Weber, you still have spirals sitting there. So that density is probably not enough to completely get rid of all the star formation, all the interstellar matter and so on. So then you can make fit SSPs to these three indices: magnesium, iron, and H beta, and you can replace them by three values: metallicity, age, and alpha over Fe, and you get this standard parameters for the objects. And so same with ages here. Metallicities are still fairly, SSP metallicities are fairly around solar. So the paradigm that was very common in the 80s, that ellipticals are super metal rich, is not really true. It's a little bit more than solar, but not very super metal rich. The same can be said about the bulge of our galaxy. It was said it's super metal rich. Forget it. It's not even solar on the average. What you do see is a nice correlation between age and alpha over Fe. So you see that the old galaxies all have enhanced alpha over Fe. That is actually something to look at later. If you then plot the diagram against sigma against these three obtained parameters, sigma metallicity, sigma age, and sigma alpha over Fe, you see a known correlation of alpha over Fe with sigma. So the brightest galaxies have the more enriched population in alpha. You see that, again, that there's a lot of bright objects with a sequence of the year. Here, what is the case is that you have multiple populations, and it's nothing to do with an SSP. So these ages are not, they don't really mean anything at all. It just means not old. That's it. And these metallicities out here also don't mean anything. Because if you might do it at home. You do an experiment, put two populations together. One, solar metallicity and a very old age. One, solar metallicity and young age. And then try to fit one SSP to it, and the chance is high that you get higher than solar metallicity. So the fact that the metallicity here is solar or higher than solar has absolutely no meaning. So if you write this in papers, I will really be, and I get it as a referee, that's not very, very pleasant. Okay. But this is a mistake that people make in lecture quite often, you know. So what you get is a little bit of this diagram. So the bright, but not high density, low density, is the bright objects apparently get formed quickly first, and the fainter objects somehow they build up in a longer period out here. So this is probably what's happening, but even probably longer than that. The figure is not exactly adequate. But. So now I'm going to say a little bit about Spitzer. We're trying to use the Spitzer for the same thing, for some scaling relations. Let's see what happens here. So this is Spitzer. These are the bands. Daniela has been talking about 8 microns especially. John has been talking about 3.6 and 8. So I'm going to talk here about 3.6 and 4.5. And you see from the spectrum, so these are stars, young star, old star, hot star, cold star. This is dust, heated dust with paths. This is an AGN. So you see that at these bands, the light mainly still comes from stars and from AGNs. And maybe if you have really a lot of this, it could come in, but not a priori. So emission 3.6, 4.5 is dominated by light from stars. That's the assumption from that figure. And if you then look at the figures of ellipticals, it's probably like that. So the reason I'm doing this is that 3.6 and 4.5 are probably not affected by extinction. They still might be a little bit. I mean, AV might be something like a few percent of, 80.6 might be a few percent of AV. But you have also what I said in the second lecture, that the dependence of these bands, what they do theoretically is very little known. I mean, people haven't studied them like in the optical for years and years. People haven't studied them in fact at all. So this is NGC 379, the standard elliptical as it was called for a long time in 3.6. It looks completely like a standard elliptical. That means that the light is probably stellar. This is the same thing as 4.5. I mean, the focal plane observes both at the same time, so that's why one is there, one is there. And so we took data of the whole Sauron sample, the whole 48. We're going to do the same trick as for the line strength sigma. We're going to do it for Spitzer. So get color profiles. Now, how to get color profiles? The problem always is the PSF. So in Spitzer, the pixels are 1.2 arc second. The forward half max, the diffraction limit in Spitzer is in 3.6 is also 1.1 or 1.2, so very similar. So the sampling, the Nyquist sampling criterion is not reached. So you're undersampled, which means that you have to be very careful what you're doing. So here we convolve the 3.6 micron image with the modeled 4.5 PSF and convolve the 4.5 image with the 3.6 PSF. These are the PSFs of Carl Gordon. Then you have a PSF which for both is the same. It's of course a bit degraded, but you have to take this into account. You have to just accept that, I guess. Then fit ellipses, so get elliptically averaged color profiles basically. And make sure that the sky you subtract is a good sky. Okay, that way you get some profiles. So these are the color profiles in 3.6 and 4.5 of a number of objects. So what do you see? Most objects go down with radius, like that. They become redder with as a function of radius. And there are some features that you see in the middle. Here's a feature, here's a feature, here's a feature. There's quite a bit of features. But in general, it looks as if you can do something with it. It's not noise. This is 4570. This is a really nice one, which goes down completely. You see, again, it gets redder, while, for example, a different color like J minus K gets bluer. And so all other colors that I've shown you get bluer. So the reason, so let's do it as an example. This is the way to really understand what you do, what's happening. This is 4526, an S0 with a big dust lane there. So you see the absorption by dust. At the same time there, the dust coincides with ionized gas. That's almost always the case. The ionized gas and young stars, of course, because they have to ionize the gas. The ionized gas these stars, the young stars at the same time can be seen here in H-beta absorption. So you see that there's this younger disk sitting there in the place of the extinction. This corresponds exactly to that disk. So this is something, this inner disk is redder, and after that, when it's done, you get a normal color profile like in any other galaxy, also getting redder with radius. So younger getting is also opposite to what you expect. The profile getting redder here is also opposite to what you expect. You can explain that by knowing that in the 4.5 micron bands, there's a huge molecular band, and that molecular band, when the metallicity goes up, the molecular band becomes stronger. So the light in this band disappears, so the color becomes bluer. So higher metallicity becomes a bluer color, and so on. So that way it's understood, and it just works the same as all other colors, except that it works opposite. These are some models. Note how incredibly complicated these models are. These are stellar population models, integrated SSP models from the Charlot and Bourgeois set. So you go down in age, going to the left, and you see that when you go to lower ages, the colors here become indeed redder. When you go to higher metallicity, the colors also become indeed redder. Well, going to higher metallicity, the colors should become bluer. So there is something wrong with the models yet. What you do see is you see a lot of incredibly, it goes up and then it goes down again. This is the phase of the AGB. So in the phase of the AGB stars are extremely sensitive, are extremely important for this. I think 80% of the light, according to models, comes from AGB stars. So also you should expect a lot of scatter in the data there. So another set of models is then the Marigo models. Here you do see that the behavior with metallicity goes the right way. And the behavior with age goes also the right way. But there's so much difference between the two models that it's still very, very tricky at the moment to apply them and to trust them. But there has to be, something has to be done about it. This, of course, is the effect of the AGNs. So you saw in before that AGNs, of course, also are important there. They're important everywhere. This is M87. M87 has this huge, well, huge not, has this very prominent jet from synchrotron emission, and you see the jet here also coming in. It has a very red nucleus in the center of a red nucleus on top of a normal, otherwise stellar dominated galaxy. Good. This is the color sigma relation here. So let me make it a bit bigger. So what we see is that if you go, so the points are colored with the optical age, the age you get from the optical data inside RE over 8. That's why there's an 8. So all the optical, say that all the galaxies that in the optical get a very old age are out here, except for a few which which go to different values. What you do see is that you have a nice sequence, and that the galaxies that are above the sequence are blue, the optically young galaxies. You could even maintain that you have a nice sequence which is flat, a metallicity sequence, and that everything here above is caused by ages, by young ages. But then, of course, you have problems with objects like this, and that, a bit of problems. But clearly, you see there is population information to be gained from here. And why is that interesting? Just because 3.6 and 4.5 give very, very high signal-to-noise image in the archive, and it's much easier to do 2D than to do, for example, using line indices. So just quickly, I'll come back to it, but quickly, what's the AGN effect? We've looked at the sample, the red sample is objects in which there's a compact 6 centimeter core to be found. This is an indication of AGN. And you see indeed that those objects are lying above the other objects. So there's a little bit of an AGN effect. So what it's doing in AGN is probably heating a torus around it, around the center, around the black hole, and that torus that's then radiating and making the color a bit redder. So this is the behavior in general of this color. Young population get redder colors. Increasing metallicity is bluer colors, AGN redder colors, and more massive colors also bluer. So these are a number of other, with the same symbols and so on, a number of other relations. Here you get V minus 3.6. This is from the paper of Falcon Barroso recently. You see similar, but the scatter out here is quite considerable. And you have also an object out here. This relation starts looking very much like the 3.6 minus 4.4 against sigma. And here you see how incredibly horizontal those lines are. That H beta completely determines the the SSP age. So if you then compare these two figures, as I discussed, I mean, it looks as if the information in this diagram is very similar to the information in these diagrams. I mean, these are objects that are away from some kind of relation which look either like this or like that or like this. And there might be some metallicity change as well. Of course, one index cannot contain a lot of more than one piece of information, but it seems similar. So let's compare the line strengths and the 3.6 minus 4.5. There is a comparison with H beta, so there is similar information contained in it, but the young population are more effective in H beta than in 3.6 minus 4.5. And this is the one with magnesium. And here you have a very similar, it's completely the same. There's a bit of scatter, but for the rest it's just 1-to-1. That really is strange. Because as I showed you before, that in 3.6 minus 4.5, AGB stars should be very important. In MGB, AGB stars should not be important. So I am thinking that there is something funny in the way that we are treating AGB stars. I have no more information, that's it. But this is just a hint for the future. This is the models. Models don't really fit very well. They come in the same area, same regime, but that's more or less it. So, taking again the AGN, let's go to the sample of spirals. I think there was a question the first day about whether you noticed the AGN in Spitzer colors. So this is from the thesis of Guido van der Wolk, who presented the thesis 2 weeks ago in Groningen with me. And it's not published yet, but you can get it online. You see, this is the red symbols are the Sauron sample of the 24 SAs. And this is a 3.6 minus 8 versus 3.6 minus 4.5. So just pay attention to this color. Indeed, here all of the values are between minus 0.1 and 0. So what I got for the ellipticals as well before. But 3 of them have very, very red 3.6 minus 4.5 colors. And those are objects that if you look at them, if you look at the radial, if you look at their classification and so on, they're undisputably AGNs. So the AGNs here affect even more than M87, affect this 3.6 minus 4.5 color very much. So this is a very good AGN indicator in principle. So even out here, you might think that you can detect a little bit of that it's the resolving power is probably enough to detect small AGNs in there. Okay, this is ellipticals. And let's now go to, we're talking about 0D, huh? Let's talking about spirals now. So this is a diagram of so now I'm going to talk about the 24 SA spirals. So the MGB sigma relation, say for ellipticals and the zeros was like that, and there were a few outliers. Now if you add the spirals, which are the blue points, there are more points below the line. Well, obvious, because spirals have more young populations. If you do it the same diagram, but now sigma versus H beta, which is a much cleaner diagram, as you can see, but there's not much data in the literature about it, you also see that most of them are going up. So, very simple. In the spirals, there's more young populations. That's not something that we learned something from. But you can, of course, go and look at the H beta map. For example, in this galaxy, you see it lies on the sequence. So it means really that such a galaxy, which has a small H beta, an old age, really falls in this line. And this one, which is really young from the H beta map, goes down here, and in this case is very high up here, and so on. So the diagrams make sense. So if you then add even later spirals, and that is the sample of Ganda et al., these are the black points, and that's a sample SB to SDs. They do more. They even go lower, and out here they go above, and so you get, this way you fill the diagram with basically a representative sample of all bright galaxies. And of course, they're even more dominated by young populations. But fitting SSPs to those populations it doesn't really make much sense. I mean, it's obvious what you get. This is probably more interesting. So here you get a diagram of these central values. This is RE/8 values versus type. So the morphological type from the Vaucouleur. So that's why some of these classified as SA by Sandwich are here. What do we see? This is actually I like this one. Red is ellipticals and that's zeros. Blue are SAs. And these are SB to SDs. Scatter in all the indices in H beta or magnesium or iron is very small for ellipticals. But going to the S0s, the scatter goes up, and even you see some objects which have very high H beta values, very low MGB values. Those form stars at a rapid rate. There's a lot of it, and it's dominating the populations. If you go to SAs, same story. So some of them look like ellipticals, some of them go down and are completely dominated by the young populations. And then go to the later types, and there everything is smooth. So everything is similar. So this about talking about star formation modes, here the mode is the mode of Kennicut is starbursting, and in the other cases it's slow. But also you see in S0s you also have this starbursting mode sometimes sitting there. Alpha over Fe. So here, these are ellipticals again. So the alpha over Fe here there's some iron against magnesium. With models of two sets, 0.5 and 0. You see that the ellipticals often, especially the bright ones, are be found at alpha over Fe is high, and the blue points that are the spiral SAs in between, and the later types are on the solar. So the later types are the late type disks, and they are like the sun. Well, that's of course the way it should be. But it's good that it's found to be like that. But also in the inner region, because that's where the data come from. So now, okay, these are average values. Now we'll go a little bit beyond the center to trying to see features. Okay. First question is: you have seen the kinematics. Do the line strength maps follow the kinematics? These are a number of objects, of course, where I can show something. So you see some of them with counter-rotating cores in the middle, perpendicular core. So these are kinematically decoupled cores. Line strength maps do not show KDCs. That's actually was already known. It was already known when people did long slit spectra that you wouldn't, from the line strength profiles, you would not see any strange or decoupled rotation. But what do you see? Well, out here there's obviously a disk in the middle, but here you see that the magnesium is very high in a region which seems to have different isophotes as the different isochromes, lines of constant magnesium, as the isophotes. This object, most of them have enhanced metallicity in the middle. I'm sorry, MGB in the middle and iron in the middle. This one has low Mg in the middle, so it's a different one. It's an exception. It's one of the young ones. Here, with this counter-rotating core, you don't see anything of it. I mean, the population starts rotating the other way, but you don't see any of it. Actually, that makes it quite boring. As a result, fewer and fewer people have worked on the kinematic, on the line strength as on the population, as on the kinematics, because it's less spectacular. So, for these 48 galaxies, this is from the paper of Kunstner et al. 2010, we find the following gradients with SSP populations. So the metallicity is going down. So the order of the population is just in order. The color is in order of age, in order of central age. So most of them, or basically all of them, have little gradients going outwards. The age is usually going up towards the outer parts, and quite a few have constant age or something like that, but quite a few also have centers which are obviously younger. And alpha over Fe is difficult to see, but it looks generally as more or less flat. Not all the time, I'll come to it. So this is this first thing. This is something which is not completely worked out. The data is not that good enough yet to really establish it very well, but what do you see? If you have objects which rotate fast, you can see it a bit. I mean, if you have good eyes, you can see that the isophotes of these objects are slightly disky. I mean, people should be able to see that, definitely if they're trained. The fact that they're disky is a good indication that it's really rotating fast. So you see soul rotation, soul rotation, soul rotation. And then you see that Mg, magnesium, and definitely Mg over Fe, is elongated and is elongated even with higher elasticity than the isophotes. And you can see it here from measurements. I mean, the elasticity of the MGB versus the elasticity of the mean elasticity of the object. And you see a number of objects that are above. So What's that? What's happening there? My idea is that you have inside these objects, you have components. So you have a disk-like component. So there's a set of orbits together, which is then a component, which is really like behaving like a disk, and it's flatter than the galaxy itself. And you could, in our galaxy is also lots of components, and it's definitely possible that there is something like that. So then we can see what the population does. The energy over Fe of that population is high. That is not something you would expect from a disk like our galaxy disk, but they're not the same. They're different kinds of disks. These objects that have these they're fast rotators and have these long elongated disks are old. Are completely old. So these are old disks, and as a result also have high alpha over Fe. But there are also other objects. So take now, this is the diagram of these objects, now also with the behavior as a function of radius, and let's take a few of them. Let's take 4 of them. And these are 4 that have known to have younger ages in the middle. So, these 4, so they rotate, of course, and they're all fast rotators, but you see that all 4, here, a nice spiral arm, in an S0, a nice disk, a nice spiral disk, and a nice disk with spiral arms. So they all have the features that are common. John showed them a few last lecture, and they're all there. This is an indication of secular evolution in ellipticals, in S0s. I don't want to say ellipticals, I think this word is a bit strange. Elliptical S0, I don't want to make the connection, the difference. All these maps are young. In fact, in this case, in this case, the whole area is young. In this case, it's also fairly young in the general. This central piece is young, and this is here, it's young. So it corresponds to young ages. With young, I mean something like 1 gigayears plus or minus 2. Well, plus or minus, plus 2 minus 1. Like that. So, young stars are connected to disk-like structures and kinematics, and and you see also sometimes young disk inside older rotating structures. So now I'd like to see, can you see these little features, these little disks, but then old? In principle, a disk is a disk, and it doesn't go away, except through diffusion, slowly, very, very slowly. But in principle, it shouldn't. There's no need for it to go away very quickly. Maybe Isaac or someone else can answer that later. How long it takes before such a small disk disintegrates. So, how do you find a little inner disk? So you do kinemetry. You fit basically the velocity field. See the paper of Reynier et al. 2008, and you see that here the velocity profiles, the rotation curve has a maximum. And if it has a maximum and then goes down, we define it as a little disk. And that's probably reasonable. So, in these disks, like a disk like that, like the previous ones, what you do find is the age is going No. So, so this would be a case, this is 5830, this is a case where the central areas, where the age is higher and the metallicity goes down. This is exception. This is a central disk, but the central disk is not young. So, look at these objects. These are, if you remember, 3414, 3608, 4458, these are all non-rotators. You see? Or, see, there's no rotation, only in the middle. And there you see, indeed, the age is all going up. And, the age is all flat, is old. And the metallicity is slightly going up, and the alpha over Fe is also the same. That means, here you have disks sitting there that are not associated with interstellar medium, that's probably all gone, that are old, that are just there, that have alpha over Fe that is high, opposite to the little disks that do show star formation, which are alpha over Fe, which is solar. So it's clearly a different kind of central disks. Remco van den Bos is saying that this is a projection of the galaxy, of a triaxial galaxy. There's nothing to do with the disk. It's just a projection of a central galaxy. But I would say that it's very, I mean, if I see something like that in the velocity field, I mean, of course, it is possible to make a triaxial model and project it in such a way that it looks like that. But is it like that? So, these are a number of conclusions. There is a connection between rotation and enhanced metallicity for fast rotators, yeah? And also that you have these components, so separate components in the elliptical, one with enhanced m alpha over v. Secondary star formation, so sometimes young, sometimes already happened a long time ago. In the young stars have enhanced metallicity with low alpha over Fe. So this is star formation happening in these young populations, happening slowly. And there's evidence of this enhanced secondary star formation about 25% of the sample. That, of course, that number has an error of, I don't know, it's 48 objects. The sample selection is not random, so it could be that is plus or minus 10-15%. But the KDCs they have different stellar populations. Now, let's go to the spirals, and John showed a number of them, showed 2 of them yesterday, and I'd like to show a few more, just to give an idea of whether they look the same as these things that we see in the ellipticals, or in the E/S zeros. So I'll give 5 examples, going down the Hubble sequence. And the 2 of them were shown also by John. So 3623 has a large bulge, but in the middle you see indeed also a little feature sitting there. This is the unsharp masked HST image like before. And this inner little disk corresponds to a rotating thing. Rotating corresponds to a lower velocity dispersion, of course, because the v square plus sigma square should stay the same. And in the populations, you find that if you look carefully, this is an old age, and you don't really see the disk. And the metallicity has a little peak in the middle. So this disk is not forming stars. It looks like a disk in a KDC. Okay, it's one. It's only one. And there is a little bit of dust sitting there. So now going to a little bit later type, but now, well, this is a different one. This is 14 with a beautiful, of course, with a star-forming ring. Depending on how you define the bulge, if you do it with a bulge disk decomposition, this is where the bulge starts. So this ring sits completely inside the bulge. So it's part of the area that people generally define as the bulge area. The profile is so what you see here in the middle. This is unsharp. This is in fact this star-forming ring. It sits there, and you see it also in. But you see, in fact, it sits. The ISM and so on sits all the way in the general in the central regions. There's no component in the kinematics, in the stellar kinematics. Gas kinematics is different. That has streaming and so on, but it's difficult to interpret here. In the populations, you see in H beta you see a ring. And in magnesium you see this ring in negative, so call it dilution. And so you find that indeed the ring is younger. You can do a little bit more, you can do this a little bit in more detail and show it here. So for example, you can do in 3 places, you can measure, you can put them onto the H beta magnesium diagram. These are profiles of the object in this diagram, and these are models, sorry, by Bourgeois and Charlot. This point C falls here. This point 1, this is a blue ring, falls there. This point 2, well, if you can still see it, falls here. And so that way you can get the ages and metallicities that way. Of course, I mean, this is the clearest example that SSPs don't really mean anything for that, for those populations. But you can get an idea that they're not all. Okay. 4274 also was shown by John. This goes later, a little bit later type. So here there is indeed, again, there's a disk sitting. This disk is in fact completely dominating this inner feature. So if you do the profile, you get a bulge with n Sorsik n 1.3, and that's the bulge is about this size from here to here. So in fact this disk is completely the same as the bulge John would call the truer bulge. And indeed in the population you see that this disk is younger, definitely younger than the rest of the population around it, and dusty as it's everywhere. So we go to later types, SC 628. This is a strange one. I don't understand it very well. So because the late types I think are people haven't studied them very well, but look at it, it's like a hurricane. There's nothing in it in the middle. There is no extinction in the middle. So it's just, and the populations are, well, they're not really young, but they're like, so this is an age, this is, it's fairly oldish. And, so this is metallicity, so it's fairly old, and even farther out it gets a bit older. But you mostly sit still in this hole of the galaxy itself. But there's no component, there's no disk or whatever seen. None seen. Intermediate age to the middle, all a little bit further out. And there's also no dust seen in the middle, further out you see it. And then you go to a later type. This is 4487. And there you see that if you look carefully, the graininess is different. Right? Even the extinction is different. So you see also no component really in the middle, although with high resolution you might find something. Fairly old ages again, low metallicity. So here maybe there's not much dust because the metallicity is so low. It's not that low, it's maybe minus 0.6 or so. But you start coming into a different regime, yeah. So, this clearly I think is here things are changing, and this probably has nothing to do with type, it has to do with metallicity, with luminosity, metallicity and so on. But for the rest, except maybe M100, which might be, 628, which might be an in-between case, situation in the early type spirals and ellipticals S0s is all the same. So, here what you say is, okay, secondary star formation again is connected to disk-like kinematics. Young stars seem to have enhanced metallicities while alpha FE is reduced. This is 4074. I didn't show it very well, but evidence is for secondary star formation in most of the sample, and no component, no extra component in these objects. So I'm going to take my liberty and take 5 minutes. Is that fine, Johan? Okay, and because otherwise in the next talk I cannot really do much. So I want to finish this off with 5 minutes on again from the thesis of Van der Wolk on the Spitzer results, some Spitzer results of the centers of these assays. So these are all kind of color maps. So he is doing all the colors, 3.6, 4.5, 5.8 up to 24. And you see for example, in 3623, in this map, 3.6 minus 4.5, you see a big ring, which is also there in the opticals, like M31, but in the middle it's fairly dead. There is just, this blue means that there's an old population. And also in here you don't see much else sitting there, consistent with the optical stuff. So that's the zoom, you can see the same thing again. 4220, very nice. This is obviously a bar seen end on, or edge on. You see here the star formation sitting there at the edges of the bar. These two, and in the middle there's not very much happening. 4314, that's the one that we showed before. So it has here this star formation in the middle here. It becomes much stronger the more you go to the infrared, of course, because there you start seeing the dust. And yeah, so you can use it for analysis. I mean, if we look at 3.6 minus 8 to see if it makes a good star formation indicator. Of course, this has already been discussed by Daniela Calzetti. And you can measure, so you see the correspondence between the maps of H beta, emission in this case, and the maps of 3.6 minus 8 is fairly good. Sometimes you have a bit of differences and so on. It's okay, it measures something different, but it's more or less indicating the same thing. Note that all of these are SAs. I mean, he put a weird kind of type there, which I don't like, but you see that galaxies show huge amount of star formation, SAs, a ring, nothing, or a bit in the middle. So there can be all kinds of things in SAs. It's very heterogeneous. So these are radial profiles of these objects. These are all 24. And if you had no star formation, so if you would be in the regime where you have, where it's dead, you would be here, only here, at the bottom. And there's maybe 2 objects which are all the way at the bottom. This is the bulge radius. So if you have the bulge, you only have 2 or 3 objects which fall like there. The rest is all having star formation. And the colors have to do with, with some classification. I'm not going to talk about it, it takes forever. And if you do this in 3.5 x minus 4.5, you see indeed also the same thing, that there's a few objects without any star formation and all the rest is going up, and then out here you start seeing the AGNs. So last plot is then something about pseudobulges, about classification of pseudobulges. I don't want to say very much about it because this has just a thesis paper and it's not really digested completely, hasn't been submitted yet to a journal, but it's also maybe up for comments. So this is Fisher and Drury and Fisher and so on, the combinations have looked at ways of classification of bulges in terms of pseudobulges or classical bulges. And they do it with the, first classically they did with the Sersic index n, and they say everything below 2 is a pseudobulge, and then later they did it with 3.6 minus 8, and so they would say, okay, well, in principle, these 2 methods should be the same, so you should have a line there, you should have nothing here, nothing here. Now, if you now look carefully, out of the Saron sample, there's many of them which are in this sample. But this sample is a sample of, so what it's doing here is you get a very high n, because you have a peak in the middle. So you do here 3.6 micron Sersic indices. You get a peak in the middle, and as a result, your Sersic index gets very high. And out here, okay, you have very few. The 3.6 minus 8 is the bulge value inside. Then, since this is a bit uncomfortable to have 2 classifications which give the same result, which don't give the same result, we then thought, okay, let's just try to use also the idea also what John says, just look at it by eye and see if you can see things which like star formation or irregularities due to extinction and so on. And then all the blue things are like that. So all the blue things are then classified as pseudobulges. Everything except 4. And that then agrees with the fact that there are so few where you see in the profiles the star formation. It's a very complicated story how to do this. Also these methods of just the color don't really work, because you get also some of them which sit there, and they clearly are stars. So I think that's enough for today.
Do you believe the results?
No, I do believe in the results, but I still find it very difficult to make an automatic way of classifying. So first of all, if you say pseudobulge is a bulge in which there is star formation in the middle, then even that way is not very easy. So, concluding for today, a lot of star formation can be found in bulges. Very few don't have any and are really classical bulges, there are very few. And Spitzer is an excellent telescope to investigate star formation in bulges. Thank you.
So 2 comments. A short comment is, I emphasized in my talks quite a lot that it's really important to use more than one pseudobulge classification criterion. The criterion that's been suggested that most often gets people in trouble has nothing to do with this. It's the fundamental plane relations. And one of the things I showed was that many pseudobulges agree with the fundamental plane relations of ellipticals, and some don't. So to only use that, you're going to get in quite a lot of trouble. This is an example that requires a bit more thinking. I, of course, have seen this for the first time only right now, so I don't really want to comment on it in more detail, but only to say that it's very helpful to use more than one criteria. 4 or 5 is really great if you can do it. The more important comment is about nuclear disks. And it was very interesting to see how you showed essentially 2 different kinds of properties of nuclear disks. I loved your data, and I agree with your data completely. In the medium and light type galaxies, the nuclear disks have the properties of pseudobulges. I used a lot of your earlier data as examples because of that. In the early type galaxies, which I didn't discuss because my job was to discuss circular evolution, not ellipticals, in the early type galaxies, the nuclear disks, as Reynier said, have somewhat different properties. They have they're as alpha enhanced as the rest of the galaxy. Their age is like the rest of the galaxy. They're quite a different collection of properties. And I think the signs are quite strongly that they're made in different ways. One of the things that I'm finding in listening to the different speakers here, and I'm stepping back from your results a little bit, is that we're really sort of at 2 different meetings here. One meeting is on secular evolution, and some of us are concentrating on that. And the other one is on galaxy formation in general. And as soon as you start talking about galaxy formation in general, hierarchical clustering becomes super important, right? And that's not in the title, but that's certainly the subject of a lot of people's talks, and Reynier is talking about objects in both classes. Since we've got this sort of dichotomy of talks here, I'm beginning to realize that what I should probably try to do in my last lecture isn't so much summarize progress as tie these 2 pictures together. And so I promise you that in my last lecture I will make an attempt to tie the hierarchical clustering stuff, including what you've been hearing together here, with the secular evolution stuff in a way that, sort of tries to put things in better perspective. And then I'll come back to those nuclear disks again.
Okay. Thank you.
Reynier, Daniela down here. Hi. So I wanted to ask you a small clarification about what you said in NG6 628. You said that there is no evidence for any trend in the attenuation, dust attenuation with radius. The center is dust-free and the outskirts they show very little dust, something like that.
No.
Okay. So
no, the center looks fairly dust-free.
Okay.
But beyond it, something like 10 or 15 arc seconds away from the center, you start seeing it again.
Okay. So, and you see, because what we study is there is a trend.
I can give you an extinction profile. This is from the paper Standard 2009.
Mm-hmm. Okay, so there is an attenuation profile.
Yeah.
Because we also find one which is peaks towards the center, but we don't know exactly in the center, and then goes down with the radius. So I was wondering if there was any discrepancy here, but if it's only limited to the inner 10, 20 seconds, maybe there's no contradiction. Okay, thank you.
It's still very strange to see a galaxy where the center has been wiped clear. It's like galaxies like the Sombrero or 7814 and so on, which have, or like our galaxy has no, well, no, it's different. Like the Sombrero or 7814, which have no interstellar matter in the center that we know of. I mean, later with ALMA we might see things, but it's just gone in the middle. And this is similar.
So I'm just going to barge in with an announcement. We have 3 people who have to see Maya now about the excursion on Saturday. Sotirios Chatsopoulos, Ariana Di Cintio, and Prayo Alcafle. You have to do it now during the questions. If not, you can't go on the excursion. Sorry.
Okay.
This is less a question, more a comment. I noticed in the Soren work, when you were looking at the galaxies that have young stellar populations, the people who do CO kind of know the name tags right away from the work of Francois Combs. And it gets really interesting about the 25% detection rate, because that's exactly the detection rate we have for finding CO in these early type galaxies. Yeah. And I wanted to basically just say it's really interesting because it means that we can trace the origin of the young stars by tracing the origin of the CO.
Yeah. Well, yeah. I mean, I guess I should have mentioned that although I had to skip certain things, but It's a bit disappointing that with current CO with the current instruments, the fraction of detections of NCO is indeed so low, while ionized gas, as I said, is 75%. So that's why I find it still hard to interpret.
Hi, here. So how robust is the slow and fast rotator interpretation against inclination?
Never completely, but I think this needs a bit more time. There will be some, there will probably be some galaxies that are rotators but are seen face on, and as a result, but on the other hand, they would then in that case probably not be boxy, and most of the slow rotators are boxy, and they would probably not be bright. And so I'm sure that soon, or this can probably already be known now, the ones that don't belong in that class can be taken out.
It's 4258. It's exactly what you...
It's 4258? Okay.
4258, low luminosity, round.
Not boxy?
You call it a non-rotator. It's got all the other properties. I'm sorry. NGC 4258 is the only example in the Sauron sample of a galaxy, of an elliptical that's low in luminosity, called a non-rotator, because of course it's exactly face on. It's very round. Okay. And otherwise has all the properties of the rapid rotators. It's the only one.
Okay. Yeah. All right.
I have a question, Reynier. You talked about stellar population modeling that doesn't do a good job on the mid-infrared colors. What is missing there? Is it stellar physics? Is it observations of stars to build the models? Is it understanding of how the populations evolve in galaxies? What do we as a field need to work on in the
It's missing later phases of stellar evolution modeling. So it's missing good treatment of mass loss. And so it needs to predict how an AGB star evolves, and that's very hard. And how much dust it sheds into the ISM, and 80% of the light in those bands comes from those stars. But as I see from the really strong correlation between MGB and this color, I find it funny. I mean, to me, it might very well be that the fraction is lower than we think. Okay.
No more questions? So let's thank the speaker again.
Okay.